What could string theory say about a universe? Can we test quantum gravity? Is there a fifth, dark dimension as wide as our red blood cells? My name is Davide De Biasio. I'm a member of the International Society for Quantum Gravity Outreach team, and I had the pleasure of discussing these questions with Dr. Miguel Montero, who works on string theory, quantum gravity, and the so-called Swampland program at the Institute for Theoretical Physics in Madrid. It's been a wonderful chat, full of unexpected plot twists. Now, it's time for you to sit back, relax, and figure out whether our microscopic space-time models can reveal anything about the cosmos we observe. Let me start with something simple. What is quantum gravity, and why do we need such a theory?
Well, I'm not sure that it's a particularly simple question, but so on one hand, we have formalism to understand what happens to gravity at very long distances. That's Newton's laws and then general relativity. They work very, very well. You know, we have general relativity has passed crazy precision tests in the solar system. It's very, very good. But we actually expect that there's new things happening once the gravitational force becomes so strong that quantum effects have to be taken into account. So on one hand, GR describes very long distances. Quantum mechanics is the theory of very small stuff, okay, where things become fuzzy and there's the alternative principle, all of that. And quantum gravity is just a shorthand, you know, it's just a word that we use to describe what happens when we put everything together. Okay. So what happens when we are looking at physics at very short length scales, so short that gravity is strong? Now, you might ask, okay, what is this length scale? And the answer is just basically the length scale with gravity becomes strongly coupled is related to G Newton. So you take the G Newton, the G Newton that you get in Newton's force law, and you get a length scale out of it, and that's the Planck length. And it's tiny. It's 10 to the minus 34 meters. So just to give you an idea, I think the length scales that we can probe at LHC are 10 to the minus 18, I think is the shortest that we can probe directly. So the reason why you get this length scale being so short is because gravity is very weak. It is so weak. Just I think like the best example to emphasize how weak it is imagine, just go in your room and jump. When you jump,
I'm lifting my arm, right?
You're lifting your arm now. Like the force of your electromagnetic force of your muscles is beating the gravitational force of a whole planet. Okay? So gravity is actually extremely weak force. And what that means is that for it to become strong, you need to look at masses and particles at energy scales which are very high or length scales which are very, very small. So that is quantum gravity. And why do we need that? Well, it depends on what you mean by need. Right? You certainly don't need it to build cars. But I think it fits into the broader pursuit of theoretical physics, trying to get a complete picture of the universe, complete picture of, we sort of want to understand everything in a unified way. And for that, you need to bring together everything, in particular gravity and quantum physics.
Well, I think that's quite complete. And let me please summarize and stop me if you don't think I'm getting it properly. But on the one hand, we have this general relativity describing the universe on large scales, solar system and beyond. And then we have quantum mechanics, which seems to be the way in which things are actually written in the microscopic world. And it's quite natural for a theoretical physics, on top of all the problems we might solve, to try to merge the two into a single theory. And I get that. But one of the reasons why theoretical physics has been so successful throughout its history is that people somehow managed to combine strong maths and theoretical insight with experimental empirical evidence, right? So what's the state of our empirical understanding of quantum gravity? And do we have any hope of, accessing it somehow directly with experiments?
Excellent question. The answer is we don't have, I would say, I am an optimistic person. Okay. I'm half full glass kind of person. But I would say that our chances of the way you phrase the question, which you phrase very precisely, can we prove quantum gravity directly? And let's add in the next 100 years, because afterwards I don't know what will happen. No, but in our lifetimes, I think the answer is no. Okay, and the reason for that is because the energy scales at which the quantum gravity effects become important are so high, and we are so far from getting that. Okay, so we are roughly 16, 17 orders of magnitude from that. And the machine that proves the highest energies that we've ever built is this LHC, which is a circular collider in Geneva. It has a circumference of 20 something kilometers. It accelerates protons to like a tiny fraction of the speed of light and just bounces them together. Okay. And even with all of that, we can only get there, 16 orders of magnitude away from gravity. And again, the problem is that gravity is very weak. So that means we don't have any hope of probing it directly today. There is a way where we might be able to measure it a bit indirectly, and that is through cosmology. Okay, so cosmological observations, so when you look out in the sky, and it's easy to understand that, because the speed of light is finite, if you look further, you're looking backwards in time. If I have a star which is 3 light years away, I am looking at how that star was 3 years ago, and so on and so forth. And if I look at the farthest thing that we can see, we are probing the very early ages of our universe. Now, the current models that we have, theories of models of cosmology and inflation, suggest that some of the patterns that we might observe at the earliest time scales are correlated with physics that people are not sure, but might have taken place around 10 to 15 to 16 GeV. So that's just a few orders of magnitude away from the Planck scale, like 2 or 3. So if it's lucky, we might observe some quantum gravity effects on that. But that's again, being very positive. And, it might also not happen. Okay. So there's no sure proof way for us to measure quantum gravity today.
And of course, observing quantum effects in early universe cosmology is not exactly what I would call a low-hanging fruit, right? This term people typically use. But I have the feeling that there's some sort of other way to get there, or other way people are trying to, pursue in order to get to know something about quantum gravity, despite having little, let me say it that way, direct empirical basis. So can you tell us a bit more about the kind of work you people do?
Yes. So as you're saying, there's we have little hope of observing quantum gravity directly today, but there is increasing evidence. Okay, and this is this is cutting edge research. This is the stuff that a bunch of us are doing right now. There's more and more evidence that quantum gravity may have unexpected implications at very low energies, at energies that we can observe today. Okay, so of course, these effects are very indirect. Okay, it's not like you're gonna clap your hands and a black hole is gonna come out, but they are still there, and we think we can characterize them. So first thing you might ask is why how could this be? Like usually, like when I do in quantum field theory, whatever happens at very high energy scales, you don't care what happens in the deep IR. Okay, there is a very important difference between any quantum field theory and gravity, and that's something that was discussed by Einstein. It was one of the motivations for the general relativity, and that's the equivalence principle. Equivalence principle means that if I take two things, they fall in the same way in the gravitational field. So the inertial mass is the same as the gravitational mass. What that means is that gravity couples to energy, and because everything has energy, that means that gravity couples to everything. What that means is in a quantum theory of gravity, unlike in a quantum field theory, if you have some particle going through on some stuff, having some mass, having some interactions, when you start looking at loops quantum loops, what are the quantum effects of other objects that can take place on that particle, you must include every object, including like very heavy black holes, for instance. Stuff that is very gravitational has an effect on that at the quantum level. And so what can happen, okay, is that the way we typically discuss low energy physics is via an effective field theory. It's like a quantum field theory that describes low energies. And so what can happen because of these virtual effects of black holes is that not every effective field theory you can imagine, not every quantum field theory you can imagine can be coupled to gravity consistently. Okay? So what we do is we like to partition the space of quantum field theories into two sets. The ones that are completely fine, but actually have some problem, in some sort of problem when they're coupled to gravity. And the ones that are not, the ones that can be coupled to gravity. The ones that can be coupled to gravity, we call them the landscape, because it's like a nice place to be. It's called the landscape. And the ones that cannot, which is the vast majority of them, it's called the swampland. Okay? So that's the key word, I guess. So people working in what is called the Swampland program, like myself, well, we are on a mission to try and determine what are the properties that theories that are in the landscape have versus theories that are in the swampland. To give you a very concrete example, okay? For instance, one thing that we have studied very recently, it's a bit advanced, but the audience might benefit from the concrete example. There is a certain supersymmetric gauge theory that is called n equals 4 super-Yang Mills, which can have a gauge group which is SUN. So that means that non-abelian gauge bosons with interactions valued in SUN.
This has to do with the number of bosons and the way they interact.
Right. The number of bosons for SUN is n squared minus 1. Okay. So for instance, SU2 and SU3 are part of the standard model. But one thing that we like to do is we like to imagine consistent quantum gravities, which maybe they have supersymmetry, and that helps us to, it's a good technical tool. And you can have maybe another quantum gravity, which is different from our own universe, that has gauge group SUN. So we believe that up to 22 is in the landscape, and from 23 onwards is in the swampland. Okay? So one can use that to make predictions in this sort of like very supersymmetric universe. I mean, this is a toy model that we used to understand, but there's also swampland constraints that we believe are true in our own universe. For instance, there's another swampland conjecture, which a property that we believe that every quantum gravity theory has, which is that there's no exact conservation rules that are not associated to long-range forces. We call this the no global symmetries conjecture. And for instance, this has implications for the standard model. It means that there has to either be a fifth force coupled to a certain conserved charge in the standard model, which is called B minus L. So in the standard model, there's a charge which seems conserved, but it cannot be exact. So that means that it's either coupled to a long-range fifth force that we need to discover, and which has a very small coupling, because otherwise we'll have discovered it already. Or if that's not the case, then certain processes that violate B minus L, like proton decay, have to happen. Okay. So you were asking for a connection with observations. That's one right there.
And we are, I guess, at the crucial point. So if I may, let me briefly summarize what we've said. And then if you're happy with my summary, we'll get to more technical stuff. So you said there's a bunch of quantum field theories like particle physics, plausible particle physics, which more or less satisfy the kind of features we usually ask such a theory to satisfy. But on top of that, we have gravity. And gravity is weird. Gravity is not like electromagnetism or the other forces. It has something more and adds something more, namely more rules theories have to follow in order to behave properly when you switch on gravity. Like if you had, a button you press, you add gravity, and you suddenly reduce the kind of theories you can work with. That's the landscape. And everything else is the Swampland, which gives the name to your research program, right? That's something you agree with? Perfect.
Yeah, definitely. And there's perhaps one more point that I would like to add, which is like, we believe the way we argue for swampland constraints or for things that we believe are in the swampland, how do we argue for these things? on one hand, we have general arguments, which are based on things like probability should be conserved when black holes evaporate and stuff like that. And so these arguments were very general. They're heuristic. They're like the Gedanken experiments that Einstein was doing to discover special relativity. And so that gives us confidence that whatever we propose as a Swampland constraint is independent of what is the precise model of quantum gravity that one has. Okay. But we believe, if we do it properly, that Swampland constraint should apply to any consistent model of quantum gravity. We have several models. We don't know which one is the correct one. But Swampland arguments, because they're based on properties that should be true in all models, should always be true, fully generally. So that's one thing that we do. And then another thing that we do is these general arguments, they are not mathematically rigorous proofs, they're arguments. So then we check them, for instance, in string theory, which is a framework that we use as some sort of theoretical laboratory to tell us whether the things that we think are true in general are true in this particular example.
So putting together the usual ingredients around which everyone more or less agrees, like you mentioned, probabilities behaving well and a set of standard principles, you formulate these ideas and then test them in specific quantum gravity models in which you can control things a bit better, right? And you mentioned, for instance, let me stress that, this constraint on the kind of gauge groups you have, right? SUN with n not going beyond 22. And this sounds oddly specific at first, but if you think about it, and please stop me if I'm getting too hyped, that's quite strong, isn't it? Because in principle, n could be whatever, and there's infinite natural numbers, right? So you're picking a very specific subset of natural numbers, namely 1 to 22. And that's super constraining. So that's really, really strong, coming just from quantum gravity.
Indeed. Of course, since you asked me about this, I told you one of the most impressive examples that we have, but this example comes with caveats. Okay. First of all, I said n equals 4 superior mills. That's a very symmetric model.
Yes.
Like if any of the people who are listening want to do research in theoretical physics, I promise you're going to hear more about n equals 4 superior mills because it's everyone's favorite model. It's like, for instance, people use it for holography and the like. It's like the harmonic oscillator of quantum gravity. But it's not very realistic. Okay. In our universe, there's no supersymmetry. So that's an important caveat. Maybe another thing that I can add for if there's someone in the audience which is a bit familiar with holography, the constraint that I told you about is about coupling n equals 4 superior mills to gravity in the same number of dimensions.
Mm-hmm.
When people do holography, they don't do this. And that's why for holography, you can have SUN for any n. But if you want to couple to gravity in the same number of dimensions, the rank has to be less than or equal to 22.
And we are still talking about something like that, right? Our universe appears to have a quantum field theory and gravity. Quantum field theory, which is not n equals 4 super Young Mills, but that's the kind of thing we want to try to do as theoretical physicists.
Mm-hmm.
So let me push this a bit further, if you agree. Namely, among the Swampland conjectures, this kind of statements you make to tell the landscape from the swampland of all sorts of forms and different ways of doing that. There's one that seems to pop up quite frequently, which is even a bit weird for someone that looks at this from the outside, which is the distance conjecture. So what kind of thing is this distance conjecture? And first of all, what kind of distances are we talking about here?
Very good. So I told you that in Swampland, we try to motivate things from very general black hole heuristic arguments. For instance, I was telling you about the idea there's no global symmetries in gravity. That is indeed motivated from black hole physics. And there's like a bunch of arguments that if people are interested in, they can just say no global symmetries black hole argument in Google, or they can probably ask ChatGPT and it knows. But there's many more conjectures, many more things that we believe are true, consistent quantum theories of gravity. And, most of the time we connect them to black hole physics. But sometimes, we can get some of these statements. Okay. They're not exactly the same, all of them. Sometimes we get them from extrapolation from string theory. or any other model of quantum gravity. In practice, string theory, because only string theory can provide you with a large class of models where you can extract universal patterns. It can provide you with enough data. Okay. In other models of quantum gravity, it's difficult to even establish like existence of Minkowski space, that space where we know where we live. So, but in string theory, you have many such models. And so there's a bunch of things, weird things, actually, as you were saying, they're very weird things that happen in string models that you would not have expected. Okay. So when one constructs string models, string quantum gravities, models of quantum gravity coming from string theory in 4 dimensions, one finds that the effective field theories that we were talking about that describes the physics at low energies, they come with parameters. Okay. So what that means is that, they're like the knobs in a laboratory. You just don't get a single quantum gravity. You get a 1-parameter family of quantum gravities. They're all continuously connected. And furthermore, this parameter that you get are the expectation values of fields, like the Higgs field. Okay. So in our own universe, we have the Higgs field is a scalar, which has a scalar potential, and it's confined at the minimum. The scalars that we get in these string theory models, which are called the moduli, they're like the Higgs, only that there's no potential for them. And so if there's no potential, you can move them wherever you like. Okay. There's no position there's no preferred position for them. So you can move them around. So you get not just one, but infinitely many quantum gravities connected by these deformations. And so, just like, if you're an experimentalist, you wake up in the morning, you go to the lab, have your cup of coffee, and say, I'm going to study what happens to the system when I put the magnetic field to 3 Teslas. Okay, and then you write down what happens. And then you say, okay, you have another coffee and say, now I'm going to go for 3.1 Teslas. And you see how the system responds, and it changes a little bit. No, maybe there's like some magnetization, some response, which changes a little bit with the externally applied magnetic field. A string theorist gets to the office in the morning, has a cup of coffee and says, okay, I'm going to calculate. You don't do an experiment, but you sort of do like a theoretical experiment, because you say, okay, I'm going to put the value of the modulus to 3. And then you compute. What do you compute? Typical things you can compute is like, what are the masses of particles when the modulus is 3? What are the couplings of the theory when the modulus is 3? For each value of the modulus, you have a different Lagrangian, different spectrum, different masses of particles. So you have your coffee and say, okay, what is the mass of the particles when I put that 3? What when I put it 3.1? The masses change a little bit and so on and so on. And, if you're like me, whenever you have any knob or anything that you can tune, the thing that you want to do is turn it as much as you can, see what happens, no? And, an experimentalist cannot take a magnetic field of 1 trillion Teslas, but a theoretician can ask what happens when you send the value of this scalar to become very, very large, extremely large. You could take it even to infinity if you like, but let's just take it very large. And so here's the thing. I told you about one scalar. We were imagining one possible scale. In string theory compactifications, in string theory models, there's many different examples of scalars. There's just not one. And there's many models. And in each model, these scalars, they are different. They mean something different in the string theory. They behave differently. Okay. So there's a large variety of knobs that you can tune. But here's the thing. Whenever we tune any of these knobs, any of these scalars, and we make them very, very, very large, a universal phenomenon, which is that the masses of states. So if you imagine that I start turning on the knob of the scalar and the masses of states start changing, what happens is that when you make the knob very, very large, they all become very, very light, exponentially fast. Okay. And there is a natural notion of distance in this space, which is essentially related to how much energy would you need to change the value of this scalar on a given region of space. Okay. But let me not get into more detail than that because it's not really important. But there's like a natural notion of distance in this space related to energy cost. And so what happens is that as you go to infinite distance, as you take this scalar and you get very, very large, there is this tower of states, of physical masses that is becoming very light exponential. Okay. So that is the statement of the distance conjecture. The statement of the distance conjecture is that whenever you have any massless scalar like that in quantum gravity, and you tune it to infinity, this tower of states becomes light exponentially fast. Okay. Now that is an extremely powerful statement, extremely powerful. Okay. Because if you are doing effective field theory, when this tower of states becomes very, very light and become very light, they can destroy the predictive power of your quantum field theory. So effectively, if you're a phenomenologist, what it's telling you is that this scalar field range that you can access within effective field theory is finite. Okay, and that has implications that might be visible, for instance, in cosmology, as we're discussing at the beginning.
Oh, and we'll get there, for sure. Thank you very much for your answer. If I may, I'll drop just a couple of questions here and there to make things a bit clear for our audience. If people watching us have never heard these kind of things, like many models coming from string theory and all that, let me push a bit on that. You said that from string theory you can have many different quantum gravities coming. You mentioned the word compactification, but what kind of stuff are you talking about? Like if you've heard that string theory is a candidate theory of quantum gravity or a theory of quantum gravity, which might or might not describe a universe, that's one. But what do you mean when you say like many theories of quantum gravity coming from it?
Yeah, thanks for the question. I should have clarified that before. The answer is very simple. It's like, when you have a quadratic equation, ax squared plus bx plus z equals 0. You learn in high school what's the formula for solutions, and it's minus b plus minus square root of blah, blah, blah. So there's one equation, but it has two solutions, right? String theory is like that. String theory is a proposed framework of quantum gravity. Never mind what it is exactly. It's, as its name suggests, fundamental degrees of freedom in some way have to do with strings. That's not very important right now. What matters is that string theory is like the quadratic equation. String theory is a master framework that gives us quantum gravity, a way to compute things in quantum gravity. But just like the quadratic equation has two solutions, string theory has many different solutions, many different vacuum. Okay? So you're right. It's just one theory. Okay? But it has many different vacuum. Each of the vacua can be different. Okay? And so that's what I mean when I was saying that string theory. I was abusing language a little bit, actually. String theory is one quantum gravity, but it gives us many different quantum gravity low energy models because each vacuum has a different effective field theory. So if you are doing like I am, you're doing Swampland. And what that means is that you're looking for universal properties, the effective field theories that can arise as the low energy limit of quantum gravity have. Something that can give you very good statistics is string theory, because you can say, okay, string theory has, a million vacua of this class. Each of the vacua at low energies has a different quantum field theory. If I, as a Swampland person, think that there's no global symmetries, for instance, it should be true in quantum field theory of vacuum 1, quantum field theory of vacuum 2, quantum field theory in all of them. So that's why it gives me many. It's just one framework, but it gives me many, many, many independent checks. You also asked, I use the word compactification. So that's about the way in which people typically construct string theory vacua. So the way people like to construct string theory vacua is a simple way. It doesn't mean it's the unique way, but it's a certain simple one, is one starts with a very simple solution of string theory, which is 10-dimensional. Okay. And for instance, if you want to construct 4-dimensional solutions like our own universe, then what you do is you say that 6 of these 10 dimensions, they are compact and they are very small. They are compactified, so to say, in a 6-dimensional, very small map. These 6 dimensions, if they are very small, you can argue that they are not visible in experiments today. And you can choose many different shapes for this internal manifold, and that gives you many different theories at low level. But this is just one way of. People sometimes say that, string theory is 10-dimensional. That is, that means it's out of the way. String theory has solutions in many dimensions. One of them is 10-dimensional. And starting from higher dimensions, we know how to construct solutions in lower dimensions. But some people, some very, honestly, very impressive, smart people, they just right out of the bat, construct 4-dimensional string solutions. That's something you can do. It's just harder. Okay? Just technical difficulty, so to say.
But when you mention the possibility of making some dimensions compact, you have to pick the size, right? Is this one of those parameters you mentioned before? Like you said, these vacua have some parameters you can tune, like, in a machine and playing, like the experimentalist with the magnetic field. Is the size of these extra compact dimensions one of those parameters?
Yes. In many cases, yes. There are some cases, it doesn't mean that you can choose any manifold. For instance, you could have one parameter could be the volume of the manifold, and another could be its shape. And depending on the details of the model, one of them might be, fixed for some reason, and the other you can move, or vice versa. But yes, typically, yes. In fact, there is there is a refined version of sort of this distance conjecture, which is called the emergence string conjecture, which says something very, very curious. So I told you there's many, many parameters that you can have in a model, but oftentimes, it's very difficult to understand what happens when you take these parameters to be very, very large or very, very small. So for instance, imagine I have part of my space is like a square, like what I'm doing with my fingers now. One of these infinite distance limits that you can do corresponds to taking a space that is getting tilted and tilted and tilted very, very, very much. So what is the physics when you tilt it extremely? It's very hard to figure out in the original description. But in string theory, something very surprising happens, which is called duality. Okay. What that means is that there can be limits where, for instance, this thing becomes very, very small, and then there is a change of variables. People are used, if you're, for instance, in The Bachelor, you are tired of changing coordinates from Cartesian to polar coordinates, right? And you need to get the Jacobian right. And if you do it right, the physics is the same, always. But you also know that depending on the problem, doing a problem in Cartesian coordinates can be insane, and then doing it in polar coordinates can be much easier, right? So different coordinates can complicate the same physics, can have a very complicated description in one system of coordinates and a very easy in another one. So dualities is the same, but at the level of fields. Okay, so instead of changing the coordinates of space, we change the fields. We do a transformation on the fields, and sometimes something which was very complicated, like understanding what happens to this space when it becomes elongated like this, in some other variables can become very simple. So one thing that we found is that whenever we take these infinite distance limits, in every example we've explored, and trust me, there's a bunch of them. There's really a large number of them. When you take these infinite distance limits, there's some duality frame, some change of variables that you make in the theory, where the interpretation of the scalar is that it corresponds to some extra dimension becoming large. Always one or more dimensions becoming large. Okay? That's true in less than 10 dimensions. In 10 dimensions, there's one extra case. But since we're mostly interested in 4 dimensions, let me not talk about that. Okay? But in every example in less than 10 dimensions, this thing happens. Okay? So there's one dimension which is getting large. So that's this is called the statement that this is what always happens is called the emergence string conjecture. And it tells you a little bit more than distance conjecture. Distance conjecture tells you that when you turn the scalars to infinity, there's a tower of states which are becoming light. And the emergence string conjecture tells you, actually, the reason why this thing is happening is because it's some extra dimension which is becoming very, very large. And if you have some extra dimension, for instance, that goes from my left hand here to my right hand here, and you ask what are the masses of particles, well, particles are quantum mechanical. They have a wave function here. And people have studied particle in a box. It's one of the basic things you study in quantum mechanics, the first program you study. And the spectrum of particle in a box is quantized. Its energies are quantized. And they go like n squared, and the size of the spacing goes like the size of the box. So if you have a box which is getting larger and larger and larger, the energies are getting smaller and smaller and smaller. Something like that happens with the masses of fields. It's a very similar calculation one does when studying mass quantum fields. And what you learn is that this behavior of distance conjecture has to do with the wave functions of the particles, which have to oscillate in here. Their energies are getting smaller. Their masses are getting smaller and smaller and smaller, precisely in an exponential way. This is what is called the key word, if somebody's interested in this, is Kaluza-Klein Tower.
Which is something that, by the way, dates back a century, way before string theory, right? It's coming back and forth in the history of theoretical physics. Now, you gave us this nice picture of a landscape of string vacua. Let's assume string theory is correct for the question. A landscape of string vacua, like each point there is a different kind of low energy solution, a different kind of physics we can observe with different particles and properties and charges and all that, a whole new world to explore. Now, a natural question that an outsider might want to ask is, where are we? Like, where do we expect to be in this space of string theory solutions? Like, if string theory is correct, one of them should describe a universe. So do we have any kind of evidence pointing at where we might be in this landscape?
Well, one thing that we know for sure, it's not proven mathematically, but I doubt you'll find anybody who disagrees with this, is that if we have this picture, let's imagine that all the knobs that we can turn, all the scalars that we can turn, and the parameters different quantum gravity vacuum, we are for sure not extremely close to these infinite distance limits. Okay, so we are not. What people have checked really is that when you go to the extremely infinite distance limits, things don't work with regards to cosmology. So you cannot, in these infinite distance limits, you don't have an accelerated expansion of the universe like the one that we observe. So there's two possibilities, essentially. One possibility is that we are in a regime where all of these knobs are, order one. Okay, we might be there. It's possible. It's also very difficult to make predictions there. So it's a technical problem, but the technical tools that we have to understand string theory nowadays, they don't, sometimes people are very smart and they find ways of saying things when the knobs are all of order one, but it just typically is difficult and requires supersymmetry and so on and so forth. And so the other thing that could happen is that we are somehow close to this infinite distance region, but not super, super close. So those are two possibilities. We don't know which one is right. But if you ask for, this is what I told you is the status, or like the thing that is like, I think, agreed upon by sort of like everybody.
Been extremely honest on that, but please just tell us what you think.
If you ask me what I think is, I told you I'm a very optimistic person. I like to get excited, and I think that there are little coincidences in our universe that suggest that we are perhaps not in the strongly coupled region. Strongly coupled, I mean, where the couplings are order one, but relatively close to infinite distance limit. Okay, and what is that? Well, honestly, the simplest thing is that the physics that we are observing is what you might call Einsteinian. So the GR is this: we are in a large space-time where gravity is weak and there's a quantum field theory and so on and so forth. Whenever you break supersymmetry, this is very difficult to engineer when all the knobs are of order one. When all the knobs are of order one, typically get like some space-times which are very interesting to study, but they don't look anything like our own universe. Okay, things are strongly coupled and stuff. Also, the standard model, the couplings of our quantum field theory are not very large. Okay, they are in. We use Lagrangians to describe the standard model. That typically doesn't happen in the strongly coupled quarks that you can use a Lagrangian. So these two things, when you look at string theory models, they typically happen when you're not at the strong and the points with strongest couple. Okay? So that to me suggests that's one thing that suggests that that we're relatively close to the infinite distance point. And if that is the case, if you assume that you're close to the infinite distance point, then there is much that you can do. Because I told you about this emergent string conjecture. The Merger-string conjecture tells you that whenever you're close to the infinite distance limit, it is effectively as if there was like an extra dimension decompacted. So if that is the case, that is extremely exciting because, um, when you have a large extra dimension, there are additional signatures that you can look for. Okay. So, for instance, one of those signatures is, imagine, let's just imagine, for instance, for the time being, there's just for concreteness, there's one extra dimension getting large. If you imagine 2-point particles, okay, if these two, suppose that the extra dimension has size, I don't know, 1 micrometer. Okay. So if these 2-point particles become they are very far away, farther apart than 1 micrometer, they're gonna feel like the Newton's force in 4 dimensions because the size of the extra dimension is very small compared to the separation. But if you put them together closer than 1 micrometer, they're gonna behave as if they were in 5 dimensions. So in 5 dimensions, the gravitational law goes like 1 over r cubed. So there are universal. I told you at the beginning, Swampland was about getting general arguments that lead to predictions. Here we are sort of like relating the things in such a way. We are saying that if we are close to these infinite distance limits, then the Swampland principle, which is the Merger-string conjecture, tells you that you should have, deviations of Newton's law at the size of the extra dimension. Then there's something very interesting, which is that these deviations are actually very much constrained. And as of today, really the one case which hasn't been, which is not excluded yet, is 1 extra dimension, and 2 extra dimensions is marginal. But here's the other thing. In a non-supersymmetric model, like the one our universe is, when you have an extra dimension, you would get, naturally, you get a relationship between the value of the vacuum energy, which drives the expansion of the universe at very long scales, and the size of this extra dimension. So what that means is that by combining Swampland ideas with observations, we can make a prediction for the size of this extra dimension. Okay. So if you assume that you are relatively close to this infinite distance limit, not super far, but far away enough. Okay. If you assume that, and you also assume experimental constraints, and this relationship that I told you that exists between the vacuum energy and the size of the extra dimension, that leads you to a prediction. The only thing that is compatible between the experimental constraints on one and the Swampland ideas on the other is that there is a single large extra dimension of size. Actually, you can compute the size around 7 micrometers, 10 micrometers. And that's a prediction we made in a paper, with Cumbrum Baffer and Valenzuela, which is called the dark dimension. I hope we don't get sued by Marvel.
But let me jump in right here, because 7 micrometers might sound small because there's micro there, and micro means small, but it's huge, even compared to the kind of technology we construct, right? We are there technologically.
Yeah.
So why haven't we seen that? And then we'll get to how we might see it, but why haven't we seen it? Like, why don't cells and bacteria and whatever else behave like they live in higher dimensional spaces?
Very good. So the what you're saying is a feature that it's not just from that dimension. It's like all kinds of models which fall into the class which is called large extra dimension models. So indeed, it cannot be that a bacterium can go into the extra dimension, because if it can, we would have seen it already. The bacteria will disappear because they go into the extra dimension and stuff like that. Stranger Things kind of stuff. So what it has to be is, if the ideas are correct, is that the matter that you and I are made of, okay, standard model matter, lives on a brane. What does that mean? What that means is that we have this 5-dimensional space, okay, and then there's one of the coordinates, which is the 5th dimension. Let's say it goes from 0 to 1. Then there's a spatial object which is localized in 5 dimensions but extends in 4, which we call brain. That's just the parallels in the field. And that's where all the standard model fields live, where you and I live. So sort of we're quite funny, okay? We are planar, okay? So it's if we were to make an analogy, instead of 5 to 4, let's do 4 to 3, which is easier to draw. It is as if you and I were living in a piece of paper, okay? I'm going to draw us, okay? That's the two of us. We live in a piece of paper, okay? And you ask, why do these cartoons don't see the third dimension? Well, because they're 2 dimensions, okay? So we're 3-dimensional, so everything. I cannot draw 5 dimensions, so this will have to do. But that's sort of like the picture, okay? And so, you can always say that there are quantum fields that live on a brain that are localized. People have studied this. It makes complete mathematical sense. But gravity couples to everything, okay? So gravity cannot be confined exactly on this brain. It has to go away as well. And that's why gravity sees the field force while everybody else doesn't. There's another thing. Okay, so you were asking me, what do I think? I about these kind of things because of little coincidences, sort of. Okay. So, this, like, you can get excited about them or you can dismiss them, and both are valid. But as I told you, I like to get excited. So here's another little coincidence. In the standard model, if you have the standard model living on a brain, okay, I told you that everything can live in a brain. Not exactly true. There's exactly one thing in the standard model that can be sensitive to stuff outside of the brain. That's the masses of neutrinos. If you have a model with extra dimension, very naturally, very, very naturally, you're going to get that the masses of neutrinos are controlled by the size of the extra. They're going to go like 1 over R, where R is the size of the extra dimension. And I told you that the size of the extra dimension is related to the value of the cosmological constant. But then I have a prediction, because on one hand I have mass of the neutrino, which I can measure. Cosmological constant I can also measure, and they are related. And of course, we wouldn't be talking about this. We would not have written the paper if the relationship did not more or less, come out right. So the order of magnitude of neutrino masses is precisely what this model would predict. Right?
And that's extremely interesting. But do you have any, because I have a lot of questions now that pop into my mind, but let me go straight to the big deal. We put like higher bounds, like upper bounds on neutrino masses, right, which get lower and lower. Do you have any experiment in mind which people are thinking about that might actually go and try to falsify the existence of this dark dimension? Let me use this crazy good name you found. Like, is there anything like in the foreseeable future we might do to go and test it?
Yes. So first of all, the neutrino mass experiments, you can put upper bounds. It could be the lightest neutrino is roughly massless. Okay, but we're not there yet. And in any case, the neutrino mass differences are of the order of what the dark dimension would predict. Okay, so in making these things precise, there's a lot of details that depend on the model. So that's why you cannot make a precise number prediction for what the neutrino masses is. What I mean is that they're all, at least one of them is going to come out more or less at this value. So you cannot use that for predictions. Also, like experiments on neutrino masses, they are improving, but little by little. So what else can you do? Well, I told you that there were some bounds on the deviations of Newton's law, on the size of extra dimensions by Newton's law. Those experiments were being carried out for many years now. And the latest result from 2021 is that if there is an extra dimension, at most it can be 1, as I told you. And its size has to be around 30 micrometers or smaller. So that's the boundary. So the prediction we got is not that far from those 30. And indeed, when the paper came out, there was some group which were interested, and they are now looking to see if they can push the bound so low, so that they can get to this value. They might not get exactly to the value, but they're certainly there. And, the bottom line is that we are making a prediction which is a factor of 4 away from the current experimental bound. Okay.
Yes.
So people can improve that. And if they improve on that, they're going to falsify the model. They're either going to find it's there or find it's not. And then, for instance, if it's not there, what I would conclude is that, well, maybe after all, strongly coupled regions of string theory. What do I know?
Okay, that would have been my question, right? Because if we find this micrometric extra dimension, of course, that reinforces in a Bayesian way, it reinforces your credence in this kind of models. But if we don't find it, this is not like a unique, unavoidable prediction of string theory in a general sense, right? It doesn't tell you have to.
It is a prediction. Okay. Remember how I argued for it?
Yes.
I argued with the emergent string conjecture and assume we are relatively far out in the modelized space. Okay. So it could be that we're in the strongly coupled order. Now, I told you that I didn't think that was so likely. And the reason why I think that was so likely is because the set of models that I sort of more or less understand that live in strongly coupled regions of the landscape, they don't have the features that space like us has, which is weak coupling for gauge interactions or for Newton. So, but this is a strongly coupled corner is a corner which is it's poorly understood. There might be lots of other stuff there that I don't quite understand. Or, it could be that there is some sort of fine tuning in the models that I don't have any reason to expect, but maybe it has to be there for some reason in the universe. And then this relationship between the vacuum energy and the extra dimension could also change.
Mm-hmm.
So the model, the idea of dark dimension is in some sense is like, what is assume Swampland conjectures, assume experimental data, and look at the simplest class of models that can fit these two things. And then you get this prediction. If the prediction fails, that means that the model is more complicated in one of these two ways. Okay. And then you learn something. Okay, you learn that the universe is fine-tuned in some other way that we didn't expect, and I would love to understand.
And that's wonderful, because in some sense, this would also shed some light on the actual meaning of the cosmological constant, right? Which is one of the big open problems in cosmology and the history of a universe, I imagine, right? This has direct cosmological applications.
Yeah. Yes, that's absolutely right. So this relationship between the size of the extra dimension and the dark energy is big news in itself. Okay. So that's something that comes out of the distance conjecture and the observations that we made in top-down string theory models. Okay. Mm-hmm. In each detailed model, we understand the technical details of how it works, but it's a general relationship. And indeed, it's not solving the cosmological constant problem. Mm-hmm. In the cosmological constant problem, the way people usually phrase it is that, well, cosmological constant is an energy density that permeates everything in the universe we have observed, and it's very small. And in particular, it's much smaller than what quantum effects from the standard model would suggest they are. Okay. So the dark dimension ideas, they don't address this. They don't tell you why that happens. It's like, well, I don't know. It's somebody else solved that. But whatever the value of the vacuum energy is, it is always tied to this size of the extra dimension. So it's still a big puzzle there, which is to explain the origin of our very small vacuum energy. But in the dark dimension, that's tied to explaining the size of the extra dimension. And that's what makes it exciting, because tying two things together is a way of making a prediction.
And this is quite natural to do, right? Not easy, but quite natural. You took empirical evidence, like the kind of stuff we have, and luckily physics is an old subject, so we have a lot of empirical evidence to constrain our model with. Plus, I'd say, and tell me if you agree, whenever you had two choices, you picked the less fine-tuned, the less conspiratorial one, right? The most natural one, like the easiest one, the one that doesn't require you to keep all pieces together.
It's slightly stronger than that.
Okay.
I think the one that happens in every string theory, in every control string theory model that I know of. I don't know models where you could tune things in certain ways so that wouldn't happen. I don't know examples of control models where something like that happens. So in some sense, it's also like it's supported by all of my statistics. Now, you can always say your statistics is just bad. You need to do better. And I agree. I am always looking out to do better. So far.
Yeah. I guess that's what you do in your day by day, right? Working as a theoretical physicist.
Of course, like everybody else.
And this kind of leads me to the last chunk of our conversation, if you agree, right? I would start with a very broad question on the field, because you mentioned a very exciting development, right? This dark dimension related model building, the perspective of performing an experiment. So a quite natural answer to the question I'm about to tell you is, okay, let's wait for the experiment and then see where we'll go. But what kind of developments do you see being promising, or do you expect to come from this? So where are things going right now? Like, we've discussed things that happened or are happening, but what about the next steps?
Well, you mean in the field in general, or in
in the specific kind of dark dimension, Swampland distance conjecture neighborhood,
yes.
Right?
Yes, very good. So even Swampland and dark dimension are not the same thing. So dark dimension is a subset of Swampland or experience.
Yes, of course.
So in dark dimension, there's been lots of developments, because as you're saying, you just don't sit down and wait for the experiment. There's many other things that you can do. For instance, there's been a lot of progress on models trying to explain, for instance, how they explain dark matter. If you have some model like a dark dimension, well, you're on the hook for trying to explain everything and see how everything fits together in the big picture. So there's been papers on trying to understand dark matter. For instance, a bunch of proposals. Some people propose that dark matter is black holes in the extra dimensions. We wrote a paper where we say it's like gravitons. There's several ideas there. Another thing that people are trying to address is what is a natural mechanism for inflation. It's like the very early phase of the universe in that dimension. And one thing that I find very, very interesting, okay, is the issue of fit forces. So I haven't written a paper on that yet because I haven't had a lot of time, but in models like dark dimension, you might expect that there's relatively light scalars, give you additional long-range forces, and those are very much constrained by experiments. There is one idea which was proposed in 2006, which is called the chameleon mechanism, which allows models like dark dimension to be compatible with experimental constraints. Okay. So one thing that one can do is to check, put in the numbers sort of, and check if the dark dimension is compatible with constraint. And this is actually a job for someone much more phenomenological than I am. So you need to be on top of what the experiments are, the models, how to map the constraints in an independent way. But fortunately, somebody did it. Actually, there was a paper just in May last year giving constraints for the chameleon for this mechanism. And there's some parameter space. Most of it is excluded. The dark dimension would be right at the center of the region, which is not excluded yet, which to me was exciting. So I think understanding fit forces in that dimension is also something that people would like to do in the future. And more generally, also a very important thing that you should try to understand, not just in dark dimension, but in any model of vacuum energy in string theory, which nobody really is addressing properly. And I guess we're thinking about it, and a lot of people are thinking about it, but it's hard to come up with ideas, is the cosmological constant problem. Try to construct any model, even if it's not our universe, any toy model where the looks of the standard model, sort of, or some quantum fields, conspire in such a way that the vacuum energy is much smaller than that. So that's a very interesting thing to think about, I think, in the context of dark dimension or generally. So that's definitely, it's a very, there's many things that people are doing now, I would say.
Well, and it's quite natural for me at this point, and that's obviously a pun on naturalness, the kind of arguments we brought up today, to notice that throughout our interview, for a few times, you treated doing physics as this sort of detective activity, right? Looking for hints, finding clues, and getting excited about coincidence. But is this the kind of thing that led you into physics in the first place, and more specifically into quantum gravity, string theory, and the Swampland? What's your origin story? You mentioned Marvel before, so what's your origin story?
I don't think my origin story is really that particular. I really, I like understanding things, understanding how things work. And I felt like I was always like naturally curious. And so, how does this work? How does this work? How does this work? You iterate this question enough times, and at some point you're asking yourself, okay, but what are the fundamental laws that describe our universe? And so I've had a drive to try and understand that. And the reason why I started doing the physics degree, for instance, was because it's not so much that I wanted to work on it. Of course, working on it is tremendously exciting, and it's great to be part of something which is that cool. But honestly, I just wanted to understand it. I just wanted to understand what are the answers that we have for the most highbrow questions, and to see what we can do. And then once I got to that, once I learned the physics that you learn in the undergrad, and you get to the cutting edge questions for which we still have no answer, there was something which to me was very heartwarming that I discovered, which is, when you are learning physics, particularly physics, I think in many scientific disciplines this happens, but particularly in physics, you often that you read these things and you're in awe. It's like, how could people solve the two-body problem in terms of these integrals? How they came up with these ideas? How did Einstein come up with GR? How did they come up with special relativity? And you get the impression very quickly also the way physics is taught and the way history of physics is taught. You get the impression that this was done by roughly like 5 people, 5 geniuses, and they all do the work and then they just do the thing. And the rest of us admire what they do. And, one thing that I really liked about getting into more research level and into academia, of course, this creates an insecurity. It's like, okay, am I good enough to contribute anything meaningful to any of this thing? And one thing that I learned is that is an entirely wrong way of thinking. Like, it couldn't be further from the truth. Okay? So you don't need to be a genius to do physics. You just need to be passionate, and you need to work hard. Yeah, you need to work hard. You need to try a million things. The way you get something worth it is you try 100 times, and it's the 101st that you get something that more or less works. So indeed, you gotta be motivated. You gotta be you gotta have, you gotta learn not to be discouraged by failures. So if thing fails, try another thing. And if that fails, try another thing. And if that fails, try another thing until you find something that works. So that is so much more important than being quick at, doing calculations. Being quick at doing calculations is important when you're in an exam and you just have like 2 hours. But in real life, it's actually very pleasant. You just go, you have a cup of coffee, you say, I don't know how to do this. Go get another cup of coffee, think about it a bit more. So there's not like a time pressure. The more likely thing, the more common pitfall is that you just get discouraged. But that is amazing because, it's like anything works in life, not just physics, requires hard work and effort. So it's not different really. So if you just work hard, you can end up doing, extremely important contributions. Of course, you also need a bit of luck. Everybody needs luck. But, you talk to people, like top researchers in our field, and they will tell you the same thing. And they are people who are passionate about physics, and they are working about it. They're working on it 24/7, essentially. Okay. Well, they think a lot about it, but that's so much more important. So you don't need to be a genius. And that to me was so great, because that means I could contribute. And I felt that I have contributed to some extent. And that is absolutely great, because this thing that I admire so much using the textbooks, okay, we are helping. I feel like I'm helping to build a stage, and anybody who is passionate, works hard at it, can do the same. And science belongs to everyone, I guess.
And this is a wonderful outlook for our audience, in particular for students listening to us. I cannot agree more with what you just said. And I take this chance to thank you once again for your time, for your help, and for your wonderful explanations. And I hope to see you soon in Madrid.
Thank you so much, David, for reaching out to me and getting me talking 1 hour on what I like most, which is physics. So
that's what I like most as well. So
yes,
thank you again. Thank you again, and see you soon.
see you soon. Thank you. Bye bye.